Okay, section 4, polynomial functions. Now we're going to start looking at the polynomial functions, particularly at their graphs, but we're also going to be doing some other things with them. But mostly we're looking at the shapes of those polynomial functions, getting just a general idea of what they look like. In the evaluating, first of all, we're going to look at some things like what the variables are. Notice all these have just the one variable r. So there's a polynomial in one variable. Now, in order to be a polynomial, remember that the exponents are important, that all of the exponents are both positive and integers. So I can't have a fraction up here, I can't have a negative number, I can't have roots, I can't have the variable on the bottom. Okay, these would not be polynomials if any of the terms include that. So all of these, this is to the second, to the 1, this would even be r to the 0 power, and so they're okay. And so these are polynomials. Now, when they write it, they say the degree of n for that polynomial, they always look at the highest power. And usually our polynomial would be written like if this one's 2, then it goes 1 and then 0. If we had like x to the 5th, we might have plus something x to the 4th, plus something x to the 3rd, and so on. We might have a term missing, like maybe my x squared is really a 0 there, and we just wouldn't even write that term, but we would still consider that x squared as being there. And we keep going down until we get to just a number on the end, like this one ends in 1. And so my degree of this polynomial, we just look at the highest exponent, the degree is 2. And what that highest thing is, that's called the leading coefficient. Okay, it's the term with the highest degree. So in this one here, that's 2 is the highest degree. Here the highest one is 3. And some special names for these, if we just don't have a variable there, it's a constant. It doesn't change. A linear one is when our power is 1, our degree is 1. And this one's x squared, so it's the power of 2. And we also have what's called the leading coefficient. The leading coefficient is the number multiplied by that first one. So here I have a 1x, so that leading coefficient is 1. Here this is 3x squared. X squared is the highest one, so 3. When we're looking at this leading coefficient, we're kind of ignoring the rest of this to find that. And so that's also going to give us the degree of the polynomial by looking at the highest power. Okay, so for example, this one, we're going 4, 2, 1. So the highest power here, this has a degree of 4, and my leading coefficient is the number in front of that, just that term. Basically, we're ignoring everything except the highest degree term. Now, the next one has a problem because we have both x and y in this. So it's not a polynomial in one variable because it has that y. So we wouldn't even answer these questions because we can't. Would we be dealing with x or would we be dealing with y? We don't know. This one, again, not a polynomial because we have something divided by x. This one is a polynomial. Be careful that the order is not in our usual order here. The highest term is 5, so my degree is 5. My leading coefficient, even though this is in front, the leading coefficient is what's supposed to be here, and that's a negative 1. Keep your negative signs grouped with your coefficients. Polynomial function then is when we have a y equal to that polynomial, or f of x is equal to that. Okay, so one way that we could use a polynomial if it's in function notation, we want to know, they ask, show that this gives a total number of hexagons when we have r equals 1, 2, and 3. So this is a function that tells, like, if I have one ring of hexagons in a honeycomb, I would just have 1. If I add another ring around there, that would be 6 more of them, plus that 1, that should give me 7. 3, I could count and add these on. So once we get bigger and bigger, it's nice to have a formula to be a shortcut for that. So in my first ring, we just rewrite this, but instead of the r, we're going to leave blank and go back and plug in whatever we started with here. And then we simplify it. 3 times 1 minus 3 plus 1 gives me 1. So that first ring just has one honeycomb in it, or one hexagon in there. We can do that again for the second ring. Just plug a 2 in for that. 4 times 3 is 12, minus 6 plus 1. Now we have 6 plus 1 is 7. So we already counted we had 7 there. For the next one, again, copy it all out, leaving spaces there. This time we're looking at 3 rings. You get 27 minus 9 plus 1, which gives us 19. So let's go ahead and count that. We had 7 already. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 rings. Okay, now, when this is really nice when we have a really huge one, like we wanted this to have 12 rings, so we're going to plug a 12 into here. And this is going to give us 432 minus 36 plus 1, or 397 of these little hexagons if we had 12 rings going around. Okay, so mostly with this function notation, we just want to take whatever we have and leave blanks in there. So we rewrite this as x squared plus 3x plus 4, and then plug in whatever we have. But if I have something bigger like this, notice this is 2 different parts here. I'm going to go ahead and rewrite it as 2 different parts. I have minus 2 times the second part here. Now within that, within each of these, I'm going to write this all out. So I have my x squared plus 3x plus 4. X squared plus 3x plus 4. But I have to consider what I'm plugging into this. For the first one, instead of x, I want a plus 1. So I'm going to plug that in. For the second part of this, I'm just plugging an a in here. Okay, so everything, I just copied it exactly as it was, except I'm substituting this function in instead of the q of whatever. Now I would need to simplify this, which would give me a squared plus 2a plus 1, 3a plus 3, minus, be careful to bring this into everything, minus 2a squared, this gives me 3a, so minus 6a, and then minus 8. So don't forget to group both the negative sign and the 2 with those. Combining like terms, we get. Okay, so once we've got this, we want to go ahead and combine things together. Now we want to be very careful here with combining our terms, make sure we get everything. So first let's look at our squared terms, which gives me negative a squared. Next I'll look at my a terms. We got 2, 3, gives us 5 minus 6, which would be minus a. And then finally, plus 1, plus 3, plus 4, it gives me positive 8, minus 8. Those are gone. Those will give me a 0 there. And so my final answer on this would be negative a squared minus a. Okay, so again, with these function notations, plug in everything. Please use parentheses here so that you don't get messed up here. Make sure that, like this term here, has to be the whole thing squared. So you'd either be using FOIL or your definition of a perfect square for a polynomial, or remembering that you have to multiply 3 times everything here. And also the signs get really important there, so please do that.